let's go ahead and get started. So we have quite a few things to cover today, just like the other day. So what we'll do is we'll finish all the practice questions for the midterm on next Tuesday, because I think that's one of the more important things before we move on to talk about the new homework assignment. So I think we'll have enough time for all of those things today. The first thing we'll do is we'll take a look at the gate logic of half adding and full adding. Okay, we've talked about those concepts already. It's just that we never really, I think I did show you the TK gate, the program, with all the gate logic. So that would be a part of the exam. You do not have to design your adder. Okay, so that's not a part of the whole thing. You do have to understand how an adder works, so that when I say, okay, if I tap this point of a full adder with multi-bit, adding, what would be the value, at that point? Okay, so I will give you an example today, as to what type of question I'll be asking. And then I also told you that we'll have a question on Johnny as well. So I will define a new instruction. I'll give you the sequence of microcode corresponding to a new instruction. I'll give you an instance of that instruction, in a particular memory configuration, and then you will have to tell me what happens after that instruction, executes. So you have to kind of explain to me, okay, this location will be copied to this location, or we'll continue execution over here. So you have to tell me what's going to happen when we execute that instruction. So those are the two things that we'll go over today, in case there are any questions about Johnny. And then there's a new homework assignment. The new homework assignment is to implement the logic to find the maximum of two variables. Now, of course, we don't have variables in this class. We have two registers. So I will give you, a particular value in one register, another value in another register. You have to specify the logic to find the maximum of the two, and to store that maximum onto a third register. Okay, so those are the things that we'll go over tonight, and we'll start with TK gate first, okay? Because TK gate is the program that I used in order to display the logic of a full adder and a half adder. So let's see if I can find that particular file first. Yep. Okay, so those are the programs. And sometimes, since I'm recording the whole thing, you can even look at some of the commands that I run to do certain things, like the command that I just ran is finding a particular file based on its file name, and somewhat like using a regular expression. It comes in handy if you remember that I know I have a file with that kind of a name, but not exactly what name it is. So let me show you the command again. This is the command that I just used. The program is called find, F-I-N-D. Dash name, it has many options. Dash name is the more intuitive way to do it. For anyone who have used like a DOS prompt in Windows, you probably know how to use wildcards and stuff like that. So this one works fairly well, but it also has a whole bunch of other options that you can search by, locating files within a certain modification time. You can based on file sizes and stuff like that. So it comes in pretty handy as a tool to find specific files that you kind of have some idea of what it is or where it is, but not exactly. Okay, so we'll use TK gate, which is a program that you can also install if you want to install it onto your own Linux distribution. Feel free. And here is TK gate. All right, and we'll begin with a half adder. And I'm hoping that this is, to most people, this is a, okay, how do we scroll this? I remember the user interface is not necessarily the greatest. There we go. Okay, so this is a half adder. A half adder has two inputs. In this case, let me see if I can magnify it one more time, but without losing track of the entire picture. So magnify. There we go. Okay. Well, it does not magnify the the letters, but it does magnify the gate themselves. So in this picture, let me just kind of point out on the screen here. This is an input. A is an input. B is an input. We have an AND gate here, another AND gate here. This is an OR gate. This is another AND gate. The little bubble here means it's a negation. This is also a negation. In other words, I'm doing the negation right before the signal goes into the AND gate. So A goes into the first AND gate without negation, but A goes to the second AND gate with a negation. B goes to the second one without a negation, but B goes to the first AND gate with a negation. Okay. So the first thing is, but how does this have anything to do with adding? Okay. This has to go back to the notes here when we talked about half adding and full adding. That's basically, what it was about. Basically, with half adding, we have instead of AB as the input, I have XY as the input of half adding. It has everything to do with the rules for adding in binary. How many people still remember the rules of adding in binary? There are only 4 rules, right? It's binary. You can only have 2 possible states for the first input. You can only have 2 possible states for the second input. So the way I represent this in binary is 1 plus 1. I'm going to turn off the line number for the time being because it's just kind of making it more confusing. Okay, 1 plus 1 is a 0 with a carry of 1. Okay. The reason why I represent it like this instead of 1 plus 1 is 1, 0 in binary is because if I represent it like this, it becomes chainable. I can perform multi-digit addition when I use the word carry, because now the carry goes into the next digit, and then it can go into the next digit, and so on. So there are 4 rules. This is the first one. The other ones are really easy. Okay, all the other ones are basically trivial compared to this one. Okay, 0 plus 1 is 1 with a carry of 0. And then 0 plus 0 is 0 with a carry of 0. Do you guys still remember this? Now, if you look at the inputs, the first column, if you look down, on the first number, the first column reads 1100. The second column reads 1010. That's our input. Okay, that's our AB or XY, depending on whether you're reading the notes or reading TK gate. So in the notes here, X is one of the input, Y is the other input. The result is 0, 1, 1, 0, and it is 0, 1, 1, 0 here. And then the end result is 0, 0, 0, 1 in this picture because I flipped the direction of XY. So the rows are listed in the opposite order, but basically it's representing the same thing. Are we still doing okay so far? This is a really, really quick recap of something that we have talked about already. So I'm not going to be very slow with this because we have some other topics to cover as well today. When you look at XY as input, and then you want to ask the question, is there a logical expression that can express R, which is the result of the summation, and also another expression to express C, which is the carry of the expression? And the answer was definitely yes. Okay, C is the easy one. When you look at C, which is the carry flag is really just the conjunction of the input bits X and Y. Because when you have a conjunction, the only time the conjunction itself is true is when both of the inputs are true. In this class, when I talk about logical expression, 1 means true, 0 means false. Are we doing okay so far? Okay. So this way, I can implement, or I can have a function to calculate the carry bit out of 2 input bits for adding using just the logical expression of conjunction, or otherwise known as an AND gate. And if you look at TK gate, I'm just switching to TK gate here, this is our carry right here. Because A goes into one side of the AND gate here, B goes to the other side of the AND gate, and if the output is just the carry flag. Okay, so that's how we can use a logic diagram
or logic gate diagram to represent a portion of the half adder at this point. The rest, which is this AND gate, and also this OR gate, implements the other bit. So switching back to here, what about the OR bit, the result bit? The result bit is not as easy. The result of adding 2 bits is going to be this expression here. In this expression, multiplication is the same as a conjunction, which is the AND gate. The plus sign is actually representing disjunction. This is a fairly typical expression that you will find in electrical engineering as well as computer engineering. They don't use specialized symbols to represent conjunction and disjunction. They just borrow multiplication and addition from usual arithmetic to represent those things. The prime is representing a negation. So in this case, it means x and not y as the first part. Let me just highlight which part I'm talking about here. So this part here is saying x and not y. The other part is not x because the prime applies to the x. This one is not x and y. And then the 2 conjunctions are joined by a disjunction. So the entire thing reads as follows. It reads as x and not y, or not x and y. Okay. So that will come up to the bit that we need in order to calculate the result. So when you look at this expression, okay, I'll just focus on this expression here, and then switch to TK gate. It becomes these 3 gates, because this one is basically representing A and not B. This one is representing not A and B, and this is the OR, joining those 2 together. So in this picture, I am simply using a pictorial representation to express the logical expression that is already in the notes here. But this, in return, is really just a logical re-expression of the basic rules of addition in binary. Yep.
So that whole thing is the 1 plus 1 equals 0. Is that like the whole half adder, or is like one?
That is one half adder.
Okay, so
that is one single half adder.
Okay.
The reason why it's called a half adder is because in order to finish adding 1 column in a regular adding, you have another thing to take care of, which is the carry from the less significant bit. So that's why this is only 1/2 of the whole story. You still have to take care of that 1 carry coming from the previous column.
And that's not considered as a half adder. Like, is that part of that?
When you combine 2 half adders, it becomes what we call a full adder. A full adder.
All right, so let's go back to TK gate, because this is where TK gate really shines. Is when you look at this whole thing, if you just put a box around it, if you put a box around this entire thing, you can call that box a half adder. It has 2 input, A and B, and has 2 outputs. One is the result bit, and one is the carry bit. Are we doing okay so far? So we are actually applying, abstraction or subroutine, if you will. Okay, we're putting one little block around this whole thing and say, okay, let's not look at the detail of a half adder. So now we can look at a full adder. So when you look at a full adder, let me zoom out in this case just a little bit. When you look at a full adder, it is the combination of 2 half adders. It has 3 input bits and 2 output bits. So let's take a look at the input bits here. A is A, B is B, same as the previous picture. So A and B represent, the same bits from the same column, the same position of the 2 numbers that you're adding. So A is contributed by 1 number that you're adding, B is contributed by the other number that you're adding. C in is the carry from the previous digit, okay, or the less significant digit. Because when you add the previous digit column, you might end up with a non-zero carry, and that has to go in here. When you look at the paths here, A and B adding will give you a result and a carry. That carry will go all the way to the output through an OR gate. Now there's an OR gate here because either half adder can contribute to the carry to the next digit, to the more significant digit compared to this one. Are we still doing okay with this reasoning? I'm just using this picture to represent something that we have done many times already in this class. This is also something that you are doing with your base 10 addition. It's just that when you do base 10 addition, all of this stuff is so implicit that you don't track it like this. Now this carry bit comes in to the second half adder. The result of the first half adder goes into the second half adder too, and then the second half adder will actually produce the one single result bit for this column of adding. So are we still doing okay so far with the full adder picture, which is made out of half adders?
And that's like each bit, going to each bit.
Right, this is one single column for an entire addition. Yep. But it has two stages. You can see, you can clearly see there are two stages. But each stage can contribute a carry to the next digit. All right. So now that we have this picture, we can now go back to the main picture, which is using, this is a 2-bit adder. We have 4 switches. If you look at the top part, those 4 the on-offs are switches, and each one is an input. It serves as a bit of one number. So if you want to, you can look at these 2 bits as one number. Okay, this switch and this switch is representing one number. This switch and this switch is representing the other number. The output, this is the result. This is bit 0 of the output. This is bit 1 of the output. And this is the leftover carry of the addition. In other words, you can look at this as the 3rd bit of the result. But since we can only store 2 bits, that bit is never stored. The one that is highlighted right now is never stored. It is only reflected as the carry flag in our I386 instruction set. Are there any questions about this?
Yep. So that leftover carry, if it's a 1, then when you go back to another, when you go to the CN of the full adder picture, that would then be the 1 also?
Correct. Well, you basically have to daisy chain this because you can see how the
That'll occur over and over again?
right, because you can see the C out of this guy goes into the C in of the next guy.
Okay.
So if I want to extend this into a 3-bit or 4-bit adder, I would have to daisy chain that carry bit so that it goes from one full adder to the next one. But whatever is the most significant one has no one to go to. So that one extra carry flag will be remembered only as the carry flag after the entire operation.
Which then will be transmitted to the next adder.
Sorry?
Which then will be transmitted to the next adder, or recognized by the next adder in the daisy chain.
But the daisy chain has to end at some point,
Okay.
right? So when the daisy chain ends, that one extra C out of the entire thing becomes what we know as the carry flag after an addition. Okay. So what might be helpful? Go ahead.
Why were there, in the adder, why were there 2 carries going to that portion?
Because each half adder can contribute to the carry. Let me show you what I mean by that. Let's see. Okay, I need. Okay, so I'm just going to add these 2 numbers. 0 plus 1 is a 1. There's an implicit 0 because there are no bits less significant than the one that we are adding at this point. Okay, 1 plus 0 is a 1. So what should be the carry over here? A 0 because I missed both chances to give it a carry of 1. Okay, so this one is a 0. 1 plus 1 is a 0. Should I put a 1 here right away, even though the second half adder did not have a chance to execute? Yep. There you go. That's why. 0 plus 0 is a 0. 1 plus 0 is a 1. Should I put a carry here right away? No. What about the second half adder? 1 plus 1 is a 0 with a carry. So either one can contribute a carry of 1 to the more significant digit, and that's why there's an OR to join the carry output of both of the half adders of the same column. So we are looking at one half of adder here, and this is another half adder. The output, the result goes here, the result goes here, but both of them can contribute a carry to this guy over here. So are there any questions about, half adding and full adding?
Why is that one like isn't it a kind of one after the zero?
You mean this one? Because it's coming from this 1 plus 1. Because we have two half adders here. The first adder handles the actual input bits of the numbers. The second half adder handles the result of the first half adder and the carry coming from the previous column. And that's why we have a second half adder.
Yeah, but it's like 2 zeros.
Say again?
Looks like 2 zeros here,
There are 2 zeros here,
but we have 1.
but that one comes from here. Either one can contribute a carry to the next one. And that's why there's an OR right here. Because you have to take the disjunction of both of the carry flag of both half adders to become the input to the next full adder. All right. Are there any questions?
The disjunction part, can you like clarify that?
A disjunction is an OR.
Okay, so or is, so when you did the one over there, instead, like you said, you could just put it down immediately. Is that because you have to do the other part of the adder and then do it?
Say again?
So like, you did the half adder, which is 1 0 on the last part, and then you said that you couldn't do the carry when you did the 1 1. You put it over at the very end after you're done with the 0. Does that make sense? No? Okay.
Okay, if I do this entire thing again, okay, I'll just do this all over again. So ask questions right when you have that question, okay? It's much harder to go back in time and say, okay, what about that and that and that? Especially when you don't have a laser pointer and I don't know where you're exactly pointing at. Okay, 0 plus 1. Now, I can do it in any order. 0 plus 1 is a 1 with no carry. 1 plus 1 is a 0 with a carry. 1 plus 0 is 1 without a carry. Well, there's an implicit 0 here because there are no contributing bits. This is already the least significant bit. 1 plus 0 is a 1, and since no one, this one does not contribute a carry, this one does not contribute a carry over here, nobody has contributed anything, so the carry is a 0. Is that okay? This one is already done here. 0 plus 0 is a 0. I don't have to worry about this carry anymore because only up to one can contribute a carry. Okay, you cannot end up with a case where both can contribute a carry. This is already done. We have 1 plus 1 being a 0, and we have one extra carry that is not stored as a result of a 3-bit addition.
So right there, when you did the 1 plus 1, like,
Yeah.
why didn't you immediately just put the 1? Like, remember how you said that you waited to put the 1 at the end instead of putting it at the very beginning? After you put 0 down?
After I put this 0 down,
Yeah. And you put it the 1 after. So the 1, is that just like space?
no. This is 1 plus 1 equals 0 with a carry.
And then when it goes down too, right?
Which one?
That was
This one?
Yeah.
No.
But it doesn't because it's 3
There's no place to store it.
Okay.
It's a 3-bit addition, so you have a 3-bit result. And this extra carry has no place to be stored, except to only known as the carry flag after the addition operation. So are there any questions about half adding, full adding, and how to kind of chain up all your half and full adders into a multi-bit adder? So as an exercise, and I know you guys have time over the weekend, because you will make time over the weekend. Do everything that I just did, but with subtraction. Okay. Oh no, subtraction. How do we do subtraction? Okay, I'll give you a hint. Subtraction, 1 minus 1 equals 0 with borrow being a 0. Right? 1 plus 1 has 1 minus 1 is 0 with no borrow. 0 minus 0, easy one. 0 with no borrow. Okay, great. Let's finish the last one that is kind of easy. 1 minus 0 is 1 with no borrow. What about the last one? 0 minus 1 is 1 with a borrow. Is that okay? So now the question is, how do we express this column and also this column here as a logic expression of these two columns as inputs? Now, in case you spend an hour on this and you still cannot figure it out, it's okay. You don't have to email me because it's already in the notes. So you have to read the notes about subtraction. All of these gates are already specified. Yep.
So will be like two's complement, subtraction.
This has nothing to do with two's complement. This is really just
XOR.
hmm?
It's XOR.
exclusive OR. The one is an exclusive OR, and then the other one is what? The other one is it is it's a not A and B. Yeah. So in the case of subtraction, you have to be more careful because subtraction is not commutative. So you do have to understand which number is subtracted from which other number. That's the only part you have to be really careful about, because in addition you can flip the order and nobody cares. But in subtraction, you got to make sure that which number is being subtracted from which other one. Sorry?
Which section are you?
Okay, well, this is the part when I will have to kind of nag everybody to say, well, please read all this stuff. Okay, so I'm backing up all the way to the main core site. Now sometimes I cannot remember where it's located either, but every single link, you're supposed to read every single one of these links. So I'm gonna find out exactly where it is. I'm pretty sure it's one of these. Subtraction, that's it. And let me make sure that the gates are also, nope, it's not discussed here. So that's not the one about subtraction. If it's in a later one, I'm not gonna ask it. Oh, okay, it is. Okay, never mind. I changed the ordering of the slides, so I cannot ask you anything about half subtracting and full subtracting. Well, more material for midterm 2.
So a exclusive work is no different from just using a single non-and gate, right? Making one of not.
That is correct. Yeah, when you see this symbol, it's nothing more than just having a not gate. So in some other diagrams, some people like to use a not gate first instead of putting a bubble directly next to the AND gate. So it's the same thing as this one. Yeah, these two are Sorry? No, I said no half subtraction. I did not say no half adders. This is also why things are recorded. I have to be very clear. So subtraction is not going to be, I will not ask you anything about the translation from arithmetic subtraction to logic expressions of subtraction. I cannot ask you anything because the slide is not in the topics that we have already covered. But I can ask you about half adding and full adding. Yep. Question? All right. So any other questions about half adding and full adding? So one thing I can ask you is I can give you a schematic picture of of the half adders and the full adders, and I can just point to one particular line in that schematic and say, if the input is like this, what would be the signal, or what would be the value at that point? Okay. Any questions? You can use a calculator, but only a simple one during the test. And I can supply, the calculators. I just, bought 20 basic calculators from Dollar Tree yesterday. So I think 20 would be more than enough. I really don't think you guys will need, that kind of computation power. But just in case someone feels more comfortable. Any other questions? No questions? All right. So now that this is done, let's go to Johnny. Did anyone spend any time to look at Johnny and the microcode of Johnny and say, I'm not quite sure about this particular microcode? Okay, so, I asked a question that has a conjunction inside and the response is false. So that can be many reasons. So let me ask the question in a more concrete form. Did anyone ran Johnny to basically look at the microcode and nope, nobody had a chance to do it?
Like recently or?
Since Tuesday.
No.
This Tuesday. Okay. All right. So what we'll do is I'll go ahead and do it first. Okay. So let's go to Johnny. And we'll run Johnny from here. And we'll have to display the control unit because if you don't turn on the control unit, you cannot see the microcode. All right, so everything that is a button here is a microcode. So that means this is a microcode, this is a microcode, microcode, here, 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 here. All three are microcode here as well. These two are microcode. I don't think this one is a microcode. I don't think this one is a microcode. Those are basically just ways for you to reset the data bus or to reset the address bus. So looking at this picture and all of these microcodes, are there any particular questions? Like, I really don't quite get what that particular microcode is doing. Yep. PC++ is incrementing the program counter. So when you execute that one microcode, which is over here, it will just bump up the value of the program counter by 1. That's all it's going to do. Yep. Micro steps. The question will be in the form of giving you the full listing of memory content, okay? One instruction that I invent, okay? And the full listing of the micro step or the microcode of that one single instruction. And I will tell you what happens when I execute that instruction, what would be the result of executing that instruction.
So the way your assignment was designed, stuff like that, like you had, I don't know, maybe 9 or 10 instructions. So
No, there will be only one instruction that you have to track, but you have to track the micro stepping and not the macro stepping. He had a question first, and then I'll answer your question. Yes.
It's just with that program counter, I guess my main question, understanding what that's doing, is how does that relate to the address bus in the process of actually running the program? Is it when you're running a loop, is it then on a loop or something? What relationship does that have to what code inserted or what task you given John?
Okay, let me see if I understand your question. The question is, or the way I understand it, is how does PC++, how is it actually used in an instruction, right? Well, the best way to find out is to find something that has PC++ in it, and then see what it does. In other words, do it by experimentation. And there's nothing that can replace spending time. So I can either present this topic as a textbook topic where you have to read a lot of stuff, really dry, boring, and in the end you still don't understand anything, or we can look at instructions that has PC++ in it. Okay, so we'll take a look at now. If you look at PC++ and you kind of go through the microcode of most of the instructions, not all, just most, you will see that most instructions has PC++ in it. That's because without the PC++, your program counter does not change. You keep executing the same instruction over and over again. So that's why PC++ has to be there unless your instruction does not intend to move on to the next one. Now, you might want to invent an instruction like that for certain purposes, like keep incrementing this thing until it's 0, then move on to the next instruction. You might want to do something like that. I just gave myself an idea, so good thing it isn't recorded too. Now I can watch the whole thing and get going. Okay, that's a great idea. Yep.
So on the exam, when you have a question about the microcode,
Right.
Are you going to want an answer, like say you have a question about a plus, are you going to want the answer to be like the low will increase by 1, or would you want an answer like the low will transfer the load to the data bus, at that point it'll go to the accumulator, then it'll increase the accumulator by 1, then it'll go copy it back to the data bus, like how
You only have to explain the final result of executing that instruction.
Okay.
In terms of what is it going to change. If it changes a memory location, tell me how that memory location is getting changed.
Okay.
If it updates the program
you want us
counter,
to like step through each microcode and
no, you don't
explain
have to
every
explain.
single
No,
microcode?
the whole point is for you to understand what each step
Okay.
is doing, but you also have to understand how they chain, how they kind of cooperate together as one sequence. So the entire instruction is going to accomplish this.
So,
Oh, sorry, I forgot about you.
My bad.
Join it. Are you going to give us the program going to give us for join here? Is it going to be like we're going to show us okay, so for each save, int, AVD, ACT, dash, BVM, we're going to explain what is it doing? Or is it going to give us like a big program, like a macro step, and we're going to do all the macro steps ourselves?
Yes. You will have to do all the micro steps.
So we have to like remember all these ones, or we have to write
You
it down
only have to
somewhere?
do the micro steps of 1 to 2 instructions there.
Micro step of what to do instruction.
Yeah.
But your instruction will like not be that good here.
I can only have up to 10 micro steps per instruction.
So you're gonna like, okay, but you're gonna say like, okay, jump or something, or you're gonna write like anything like int, or if you like know all the methods of those things.
Okay, how about this? I give you an example. Okay. So your program, or the way that your question is presented, is going to look like this. So the first thing I will do is I will have to make my own instruction, because the whole idea is to give you an instruction that you have not seen before, so you cannot just memorize. Some people can. I can never do anything quite like that. But some people can look at something like this and memorize the entire microcode specification of all the known instructions of this architecture. Now, there are really not a whole lot of instructions here. I think there are only 10 instructions, but I cannot remember a single one. Okay, if you ask me and say, Tag, can you recite no op of this architecture? And I can tell you honestly, no. Okay, so the whole point is not about memorization. Okay, so let me just go ahead and create a new instruction first. So I'll create a new instruction called tag. Okay, very egotistic instruction. And I'll say, okay, let's go ahead and record it. Okay, so when it's blinking like this, we are recording the sequence of stuff that I want to do when this instruction executes. So instead of making it a very meaningful instruction, I'm just going to randomly poke some buttons. So I'm going to say, let's do, okay, and then I'm actually doing something reasonably, okay, put it into the accumulator, and accumulate back to the data bus, PC++, reset the microcode to 0, and that's it. All right. So now I have just invented a new instruction. Okay. So in your test, what I will give you is the microcode sequence of this new instruction. So I will give you exactly what you see here on the screen: INS to AD, RAM to DB, and so on. And on the side, I will have a table to kind of give you the explanation of each microcode. Okay, and I will use the hover over text of each one as the clue of each one. So basically, it is just the same as running Johnny itself, except you cannot run it when you have the exam. So I will give you this part here, and then what I'll do is in the memory content, I'm going to give you the exact content at the time when the instruction executes. Okay. So what I'll do is I'm going to go here, and I'll say, let me change this location here. So the first instruction is tag, not take, but this one is actually tag. And the low part here is going to specify 0, 0, let's pick 4, okay? And then at 0, 0, 4, I might give you a particular pattern. I might not give you anything other than just 0, but I might give you something like, just 10, okay? All right, okay. Oh. Yeah, it doesn't track when I'm running through Wine, sometimes it doesn't track the mouse clicks very well. All right, so the question now is when I reset, let me just go ahead and reset the macro instructions. Oh no. I have to reset Johnny. It has crashed, and I didn't have a chance to save it. Okay, so let's just kind of simulate that. We'll simulate the simulator because the simulator has crashed. Okay, so instead of so this is going to be something that I can present to you. Is I will tell you exactly what the tag instruction has as microcode, and then I will give you a program that looks just like that, and I will tell you that you're now at location 000. Execute that instruction and tell me what it is going to do. Okay. So that means you will have to know what each and every single one of these will do. But you also have to keep track of the sequence of how they're kind of linking together.
Like if you have in the PC to AB you have one it's going from PC to AB, it's the one right now. The program counter has one right now.
Right.
If it goes up this, it's going to make address bus 001. So if you tell them in there, like now the address bus is 001, and then the next step, if it takes to RAM and DB. So that's how the data bus is at 001 also, 00001.
The data bus will have the content at the location.
Yeah.
In other words, when you specify something to the address bus, either through the instruction register to AB to address bus, or program counter to address bus, every time you have something going into the address bus, it's the same thing as flip into a certain page. I give you the page number, you flip to that page. That's what those two buttons are doing. The only difference is where are you getting the page number? Are you getting the page number from the instruction register, or are you getting the page number from the program counter? Now the other two buttons, let me just kind of point it out on the screen here. The other two buttons, which is DB to RAM and RAM to DB, is basically asking, am I reading the content out of a page, or am I writing back to a page? The page that you have already flipped to because of an earlier action to flip to that page. Okay? So are there any questions? Yep.
What does stop do?
Yeah, it has stopped execution already. Let me see if I can just reset this whole thing. I would have lost my program, but that's okay. It's not that part is not a big deal.
Also, will you be using any macrocode instructions other than the one you create in the exam?
The macro code?
Yeah, will there be any other ones other than the one you create?
You mean microcode or macro code?
Macrocode.
Well, I just invented, a kind of somewhat random macro code.
I mean, on the exam, will it be only the one you create, or will it also be?
Oh, will it also be the ones that are already defined?
Yeah.
I'll probably just be using the ones that I defined. So you only have to track at the most, 2 instructions, probably just one. Okay, so someone was asking about this button. Reset ALU, that's all it's going to do. Yeah, reset ALU is not going to be useful because we hardly need to reset the ALU. Are there any questions? Yep.
You are going to have the fetch window, right?
The fetch window?
The fetch for fetch.
Yeah, the fetch part is by default. I mean, those 4 cycles. Yeah, those 4 has to be there, and you don't have to explain those 4. Because the fetch instructions, or the 4 fetch microcode, is what needs to happen in order to get to the instruction microcode that I specified. So you can kind of assume that part is always there, and you don't have to explain that part. All right. Any other questions? No other questions? All right. Now, to prepare for this part of the exam, I think using Johnny is the key. I mean, it doesn't really help a whole lot if you just read the documentation. You actually have to do it to find out what it does. Write your own program. Okay, go through the instructions that are already provided. Write your own program. execute one instruction at a time, and then go through the entire sequence and see if you understand what the instruction is going to do. This one here is a checking for 0. Okay, so what this box does is it is saying, if the accumulator has a result of 0, then go ahead and increment PC++. Increment program counter if and only if the ALU or the accumulator has a result of 0.
Does that mean the high and the low is both 0?
Correct. All 5 digits they have to be 0. So this time, for midterm 1, I will only ask you guys to track a microcode sequence that I'm writing. But I think in the second exam or as a homework assignment, I might ask you guys to write your own microcode. I will give you the effect that I want, and then you guys will write the actual microcode to perform the operation. So instead of being able just to trace it, you have to actually design it. So that would be kind of like a fun thing to do. How many people are planning to transfer to UC Berkeley? And do you guys know what is the final year project in their ECS program? Electrical and computer science.
Probably writing something in.
You're going to write the specification of a fairly modern 32-bit processor. Yep. So this will look like a toy. If you look at the final year project at UC Berkeley as a very simple simple-minded remote control car, this is your most basic wound-up toy car. Yep, it's got 2 wheels, it has power, it can move, and that's about it.
The comparison, I would think it'd be more like when the caveman first chipped the wheel out of stone in comparison, because this is very simple.
Well, yeah, but at Berkeley, you'll still be touching the stone, except it's not the stone, it's called the model.
The liberal arts computer science probably doesn't go through that, right?
Probably does not. I have no idea. But I know enough people graduating from Berkeley that I know that final year project has always been like this. All right. Any other questions?
I'm gonna find a new school.
No, I think it's not a bad thing to do. The company that I used to work for, they were hiring people with the experience or the know-how of designing a new processor. So there's people do that. Question? Yeah, Intel.
You can say that less condescending. Maybe.
Intel! Dun 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 dun. Yeah. Sure. All right. So we have the gate question of half adding and full adding, and I promise you that I cannot ask anything about subtraction because I did not go over subtraction in terms of gate logic. There's Johnny. There's find it type of question. So are there any questions about find it both of those homework assignments? Yep.
Just a general question. Can you download TK gate on Windows?
That's a very good question. I think in Windows the easiest way to run it is to run it in a simulator, in an emulator running Linux. But
You say that's the easiest way to run it in Windows.
because I think it's that's the second easiest. The easiest is to install Linux on the computer and then run Windows as an emulator. That will make it easier. Yes. Thank you for correcting me, Chris.
No problem.
Okay, TK gate, depends only on TK, which is a particular programming language. So the key is how do you get TK to run in Windows? Because as long as you can run TK, it will run in any environment with TK. So if you want to run it in Windows, I'm just lazy, If someone has figured that out already, I'm not gonna.
You gotta have Cyanogen.
Yeah, Cygwin. So you will need to install Cygwin along with X11.
It's a lot of work to do, but it is doable. It can be done.
In other words, nuke Windows, install Linux.
No, Sigwin is not quite that bad.
You can download Circuit Maker. I'm pretty sure that works.
Say again?
Circuit Maker. Circuit Maker.
Circuit Maker. Okay. All right. There's no particular value of actually installing TK-Gate unless you plan to run the simulation, because otherwise it's just pictures and documentation. All right. Any additional questions? Let's take a look at your new homework assignment. I know you have a test on Tuesday and may not have all the time in the world to. Go ahead. All right.
It's still early, so we can get extra study.
Yeah.
I'm making good suggestions over here.
Very. Okay, so where did I stash that homework assignment?
It's below exam 1 and topic 5.
Oh, I put it in the wrong place. Okay. It's up from divide. I'm hiding divide, and this is FindMax 2. FindMax 2 does not mean it's version 2 of FindMax. It means finding the maximum of 2 variables instead of 3. Okay. So this is, the program format is about the same as all of the other homework assignments. You download a zip file, and then you unzip it, and then you look at the source file. The source file, is going to document what you're supposed to do. So let's take a look. Let's take a quick look at this. Okay. So we have, findmax2.tar.gz as the file that you download, and I'm going to open it up. It's faster to do it using the command line. It's called FindMax2. I'm going to use mouse pad to look at the file. All right.
Turn on line.
Turn on line number and change the font size just a little bit so that it's easier to read. So select font. Let's pick 15 and see how that works. More or less. Okay, so the instruction is already in the file itself. Implement the logic to find the maximum of EAX and EBX, and then store the maximum in ECX. Those are all three are registers. In case you need a refresher, one way to implement this logic is to use a conditional statement. And the conditional statement is actually in almost full C compliance, except for the missing semicolon here. If ECX is less than EBX, copy EBX into ECX, else copy EAX to ECX. Okay, is that okay? So it's not really, I wouldn't call this really complex logic. So what you need to do is to find out what instructions in assembly will you need in order to perform these operations. So I can tell you what instructions or what type of instructions you will need. You will need compare. You will need conditional branch. You will need unconditional branch. You will need the move instruction. Okay, 2 move instructions to be exact. 1 compare, 2 moves, 1 unconditional jump instruction, and 1 conditional jump instruction. Well, potentially 1, potentially several, depending on how you want to implement things. But the most important part is on line 8, it says right there, in case you need to know whether the numbers to be processed are signed or not, they are. In other words, they are signed. Okay, so we are dealing with signed values here. Okay, so you kind of have to think about, why would I need to know whether the numbers are signed or not? Does it impact what instruction I use for compare? Does it impact what instruction I use for the move instruction? Or what? What is sensitive to whether the numbers or the values being compared are signed or not? Well, the flags are the ones that are important. Okay, so you kind of have to look at the flags. Okay. So are there any questions about the homework assignment itself? And you can compare, register to register is fine. Okay, you can move a register to another register. You can compare a register with another register. All of those combinations should work well without any problems. The only time you cannot do, there are certain combinations you cannot do.
like the immediate operand cannot be a destination. Okay, that's a given. Memory operand, you can only have up to one memory operand per instruction. Okay, if you use up one for the source, the destination cannot be a memory operand. But in this case, they're all in registers. The way I grade this one is I will give you a script. The script will set a breakpoint at L1, and then L1, my script will set particular values into register EAX and EBX. Then my script will have a continued instruction to continue execution at L2, because I will also set up a breakpoint at L2. And then at L2, I will compare the output, which is ECX, to the value that I'm expecting, and see whether they match or not. Okay. In case anyone is curious of how we can do this by a script, I'm also going to show you exactly how that part is done. Okay. There's a script here called simplecase .gdb. So if you look at that file, I'm going to use mousepad for that purpose too. Mousepad simplecase.gdb. It is as if you're just typing those commands by hand. So the first thing I do on line 1 is BL1, setting a breakpoint at label L1. BL2 on line 2, setting a breakpoint at label L2. Line 3 is run to actually start the execution of the program. Assuming the program runs, okay, it will stop at label L1. And at that point, I will use the set command to change register EAX to 2 in this case. And the next instruction sets the register EBX to 4. Now those two registers have a prefix of the $sign because in GDB it does not recognize the % symbol. It only recognizes the $sign symbol to say, oh, whatever is after the $sign is special. In this case, they are special because they are registers. Line 6 types C, which means continue execution at full speed. So that should get to label L2. And by that time, when it stops, on line 7, I will print the value of ECX as the output of this particular debug session. And I don't have any need to continue the entire program. So Q will quit the debugger, and that's the end of it. So you can actually do this even with the template the way it is. Okay, I can show you exactly what I mean by that. Okay, assemble the program, AS gsteps-O, find max 2.0, find max 2.s, LD-O, find max 2, find max 2.0. And now I can run GDB, except this time when I run GDB, I'm going to run it in a slightly different way. The first part is identical to the usual way, but I can run it with the redirect symbol, which means the input or the commands going into GDB is no longer coming from the keyboard or the console. Instead, it is coming from a file. And that file is just the file that we were looking at before, simplecase.gdb. And you can see that I can just press the enter key, and it runs the entire thing. The output in this case is $1 equals to 0. That is the actual output of the entire program. Now it doesn't do a single thing because I didn't specify any code to do anything. Yep. This assignment is due next Thursday. Yeah. Next Thursday. You have 1 week to do it. But this is a part of studying too, in a way. I'm an evil man. Put your back in.
There you're orange. The red one.
Potato, horn, the whole 9 yards. But don't forget the cake. I need the cake. The cake is the key. Yep. I have not decided on the number of questions, but there will be the types that we talked about. Extra credit one. Okay, so here's the question. The question that you might want to know is, will there be extra credit questions in the exam? Okay, the answer is, it may or may not be advantageous to you. Okay, it all depends. In my years of experience of teaching this class as well as some of the other classes, extra credit questions, or when people know ahead of time there are extra credit questions, it will do one of two things. Some people will try to answer every question anyway. Okay? And some people will look at all the questions and find out, okay, this one looks kind of tough, I'm going to skip it. Okay? I'm not sure whether it's going to be helpful. What do you guys think? Having one extra question. Okay, I'm not even going to tell you which one is extra. Of 5 questions, answering 4 completely and correctly will get you a full score. Is that kind of how you guys want to set it up? I mean, I can do it that way. Sure.
You don't tell us that you don't put extra credit on there. You just, one of the questions you omit, but you don't tell us that you're going to.
No. Well, the way it works with extra credit is if you do answer all of the questions, you will get more than 100%. So if there are 5 questions, but only 4 is needed for 100%, that means if you answer all 5 questions, you get 125%.
Look, I've had you for 3 classes. I don't want to know what extra credit's going to be on one test.
So I can have one extra question basically, so that you at least you can choose. You can choose. Okay, I think I will skip over this one.
But that doesn't mean you make all 5 really hard though. That doesn't mean you make all 5 really hard though.
I usually don't try to make it really hard. Don't try. Just come naturally. All right. So are there any questions about the things that we have talked about up to this point? If there are no questions, now we'll focus on how do we actually compare signed numbers, or what is the actual outcome of comparing numbers, and what do we do after a compare instruction? Okay? Does that seem like something that might be important for something that you have to do in a week anyway?
Yes.
Yeah. Okay. Well, that's why we have the homework assignment due in a week. Because if it's due in 2 weeks, nobody's going to care. It's like, okay, lecture's over. Time to go home and have dinner. But now everybody is listening, which is great. Okay. All right. So what we'll do is we'll start with a sample program. And I'll just call that compare1. Not compare long. This is compare1.s. And we'll go ahead and write a very simple program for this purpose. .text, .global _start, _start. I'll just go ahead and copy one value into a register and then do a compare with the other one. So we'll copy 25 into E. Let's do byte operations instead. Okay, this is probably be easier. AL, and then we have compare long. Let's say -5 and AL here. Move long $1 to EAX. This is just the exit code. Definitely not required, because I don't really trace the program beyond that point. But I'm going to put it here anyway, just for this program to be complete. Okay, and I'll go ahead and show the line numbers, so this way we can refer to the line numbers when I try to run the program without using a computer first. Okay, first of all, I know what you're saying. So keep your question because I want the rest of the class to find out. Okay, because I know you know the answer already. You just need me to confirm it. Okay, so let's go ahead and run this program by hand first. Okay, for something like this, we should be able to do it by hand, find out what the result should be, and then run it in GDB just to verify. Okay, that exactly is what happened. That's the way I would approach this class, is to design simple programs like this one. Okay, theorize and find out. Okay, I think this is going to be the result of this sequence. So by the time you get to line 8, when I use IRE flags, I should see the carry flag, or should I see the overflow flag? Should I see the sign flag, and so on? So I want to predict all of those things before I actually run this program. That hand was there for a reason. Okay, so he was trying to ask one question. The question was, there's something wrong on line 6. Okay, now this is actually not a big problem. Line 6, even though it has a problem, it's not a big problem because the assembler would actually catch it in this case. So let me run the assembler first. I'm not, okay, I will go through the whole sequence. G-steps-O, CMP1.O, CMP1.S. What do you think is the problem? Go ahead. What do you think is going to be the problem?
-2.
Hmm?
-2.
Nope, -2 is not the issue. The problem is online. Go ahead.
You put CMPL.
Yep, I put CMPL, but yet one of the operands is a byte. Exactly, they do not agree. And that's exactly what the assembler is complaining. The assembler is complaining that on line 6, we have an error. An error is not a warning, okay? An error means you don't get an object file as the output of the assembler. So you have to fix this before we move on. AL is a 8-bit register. You do not specify an 8-bit register when you use the compare long instruction. So you can fix one or the other. You can either fix the instruction itself to compare byte, or you can change the register to a 32-bit register, in this case EAX. Okay. Now since the first instruction is already a byte-wide instruction, I'm just going to fix the instruction itself, so it is compare byte instead. Okay? And this is the easiest kind of problem we have to deal with, because the assembler is catching it. Okay? You know, the problems that the assembler cannot catch and the linker cannot catch, those things are more nasty because the tools cannot help you. All right, so let's go ahead and take a look at this one and say, what would be the result of this? The compare instruction is the same thing as a subtract instruction, except the result is not stored in the second operand. Okay, so you can treat the second instruction, the compare instruction, as if it is just a subtract instruction. It is the same thing as a subtract byte -2 in the immediate mode from AL. So we are subtracting the first operand from the second operand. What do you think is the result of this operation? What kind of flags should be set and what kind of flags should be cleared? Let's do it, you know, in Notepad. So this way, you know, it is captured by the screen recorder as well. Not this one. Not this one. Okay, let's close. Start a new one. There you go. All right. Okay, what do you guys think? We have 25 minus -2. 25 in binary is what? 0, 0, 0, 1. So that takes care of the 16, and then we have 9 remaining, like that. Yeah, that looks right. It is 3 times 8 times plus 1, so that looks right to me. What about -2? -2 in binary is what?
It's 1.
Well, it is.
Negative.
Well, yeah, 2 is easy to do in terms of 2's. Go ahead.
1, 1, 1, 1, 1, 0.
Yep. All ones except for the last 0. That's -2. Because when they're all ones, it's -1. If you subtract 1 from -1, it is -2. So that's one way to look at it too. Okay. All right, so let's go ahead and do the subtraction here. And I'll use the half subtractor concept here. So in this case, you know, 1 minus 0 is 1 with no borrow. And I'm going to have to take up all this space. You know, there's no borrow with this position. This one has, you know, 1 borrow. This one has 1 borrow. This one does not give me any borrow. Does not give me any borrow. This one is a 1 with a borrow. 1 with a borrow. So at this point, I'm done with the first stage of the subtraction. Now I'm moving on to the second stage of the subtraction here. 1 minus 0 is a 1. Neither contributes a borrow, so there's a borrow here. There's no borrow here. 1 minus 0 is 1 without a borrow. But since this one is already contributed by the borrow because of the first part here, you know, this 0 minus this 1, so we have 1 minus 1 being a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 1 minus 1 is a 0. And I forgot one here. 0 minus 1 is 1 with a borrow. So we have an extra borrow here, and then 1 minus 1 is a 0 down here. Okay? All right. Does that make any sense? In other words, what exactly is the big pattern 0, 0, 0, 1, 1, 0, 1, 1 representing? 27. 25 minus negative 2 is 27. Does that make sense? It seems to make sense. Okay. So, all right. So everything seems to work out. But what I'm really interested in is not even the result itself, because remember, in a compare instruction, this is not stored anywhere. We do not store the result after the subtraction in a compare instruction. So what I'm really interested in is what is in the carry flag here. What do you think? It's a 1 because the carry flag and the borrow flag are exactly the same thing. Okay, there's only one flag. It is being used for both purposes. What about the Z flag? Z flag is the
0.
is a 0 because the result is non-zero. What about the sign flag?
0.
A 0. What about the overflow flag? Does the sign of the result make any sense? When I subtract a negative value from a non-negative value, ending up with a non-negative value, does the sign of the result make sense?
No. Yes. No.
Yes.
Yes. Yes. Non-negative minus negative is basically just adding, ending up with a non-negative value. It's okay. It's fine. So when everything is okay, the overflow flag has a 0. So the prediction is only the carry flag will be reflected when I do IR E flags. And now we can actually go to the command line here, reassemble the program, and this time I have to link it CMP1 from CMP1.0, GDB CMP1, list the program, put a breakpoint on line 8 because I just want to look at the result of the comparison. Run the program, IR E flags, and only the carry flag out of those 4 is reflected here. We don't worry about the P flag, A flag, or the I flag in this class. So are we doing okay so far? Okay, the GDB, GDB is great for verification purposes, but I would not use GDB to explain why something happens. Okay, it is not a good mechanism for explanation purposes. Is that okay? But what is also important to us is, but what is the result of the comparison? In other words, is -2 greater than 25?
No.
Nope. Okay. And so I think some of you probably still remember last time we talked about the less than flag. The L flag is something. We utilize 2 flags in order to come up with the result of a comparison for signed numbers. Do you guys remember that? Which 2 flags are we using? The sign flag and the overflow flag. But how do we combine these 2? What operator do we use here to combine these 2 flags?
Exclusive.
Exclusive OR. Thank you. Very good. Okay. So exclusive OR means, it means that the L flag is set if and only if one of these 2 is a 1. So you can have the sign flag being a 1, the overflow flag being a 0, then the L flag is set. You can have the S flag being a 0, the overflow flag being a 1, and then the L flag will still be a 1. But for all other cases, the other 2 cases, the L flag is a 0. The L flag is kind of like a carry flag. It is called the L flag because it's less than. Now, this is the other part that tells you something about how to read the result of a comparison. Okay. I'll give you a general template for a compare instruction here. So let's say we have a compare instruction. I don't even bother to give you the width of the operation because it is not relevant for this discussion. There are always 2 operands. We'll call those, we'll call it A and B. And then you always have a jump instruction here that has some gibberish here to a certain label L1. So the question is, how do we read this combination? Under what condition is it going to branch to location L1? I know we are using the result of a comparison in order to determine whether we continue execution of L1 or the instruction right after the conditional branch instruction. The question is, how does the question mark come into play in this particular combination? So I will repeat this multiple times, but this is the first time I'm going to say it, and then you probably want to remember it and experiment with it right after class, because this is what you need to know to get your homework assignment done. And once you understand this part, the rest of the homework assignment is not going to take you much time. It really is not. Okay, so this is basically the same thing is, okay, this says the following. Continue execution at label L1 if and only if, okay, I have to remind myself too, if B is blah blah A. Okay, there we go. What do you mean by B is blah blah A? Okay, well, let's try a few combinations. Okay, let's try a few combinations. So let's say I have this instruction first, move a 25 into AL, compare long 25 AL, and then we have JZ to L1. This instruction or these instructions basically, or if you focus on these two, it is basically saying, continue execution at L1 if and only if 20B is AL is 25. Does that make sense? If the Z flag is set, we branch to location L1. But when do you think the Z flag is set after the compare instruction?
Subtract out to 0.
If the result of the subtraction is 0. But how can you make the result of the subtraction 0? They have to be the same numbers. In addition, there are multiple ways to make there are two ways to make the result 0 in a byte operation. 0 plus 0 is 0, but 80 in hexadecimal plus 80 in hexadecimal is also 0 in addition. But in subtraction, you don't get two choices to make it 0. You only get one thing that can make it 0, meaning both operands of the compare instruction must have the same value to make the result 0. Okay. All right, so let's take a look at another one. Now this is also another chance. Okay, I'll just look at the compare instruction itself. So in this case, I will say AL, EL, and then the conditional branch instruction is going to be A. Okay. Okay, what is JA? We have never talked about JA. Well, that's exactly above. Yep. Okay, so this is also a, I use JA because I know we have not talked about JA. Okay, because I want to point out where can you find out all the conditional branch instructions. It's all in topic 4. When you click, jump instructions, this will give you pretty much, all of the conditional branch instructions. This slide here, 6.2, particularly will give you a list of all the conditional branch instructions. These are the simple ones. You look at this list here and go like, wow, there's a whole bunch. How can I possibly remember all of these conditional branch instructions? Well, you can tell me how you can remember all of these instructions. How many flags do we have? 4. Okay, we have the overflow, sign, carry, and 0, right? And how many instructions do we have here? 8. 4 and 8. Negation, that's right. So 1 will branch if and only if the flag is a 1. 1 branches when the flag if and only if the flag is a 0. Okay, JC will branch if and only if the flag is set or has a value of 1. JNC jumps if and only if the carry flag is already cleared. So that's why we have a pair for each flag in this case. So that accounts for 8 instructions like these. What about the other ones? Well, we have the combination ones. JL and JNL is a pair, and this makes use of the fictional L flag that we are talking about now. Okay, which is really great because without the JL and the JNL instruction, you will have to make combinations of the JO, JNO, JS, and JNS instructions. Not that it is not possible, but it certainly is not as convenient as JL and JNL. And then we have JG and JNG. These are also for signed comparison. And then on top of these, we have JA, which is jump if and only if above. Now, when we use the word above and below, they only apply to unsigned numbers. Okay, an unsigned number is above another one, and an unsigned number is below another number. Right? So let's get back to this instruction here. So the way we read this instruction is, okay, I'm going to borrow this template here. Continue execution at L1 if and only if the second operand, which is BL, is above AL, which is the first operand. Are there any questions about line 32 of the mouse pad?
Above is greater. It's greater.
It's almost the same as greater, except it is only usable in the context of unsigned numbers.
So just to make absolutely clear, if we're using the is greater than jump instruction, and we are comparing with a negative number, it'll think the negative number is greater. But if we use the above, it'll see that the positive number is greater.
Backwards.
Oh.
Other way around.
Yeah.
Because it'd say -2 is above 25.
Yeah.
Now those are great questions to ask, especially when you're studying, when you're reading the notes, those are all great questions to ask. So after you think it for a while, you think, okay, I might have a good understanding of this material already, write a 5-line program to test it. Okay, because writing the 5-line program has 2 advantages. One, it can confirm whether your understanding is correct or not. And then 2, it gives you an extra chance of practicing all the commands and keys that you need in order to use GDB. Because I know the purpose of this class is not this is not CISP 365 how to use GDB, but knowing how to use the tools well is going to be helpful. So it's a great way to experiment.
If you were to set BL to -1 and AL to 5, this will validate the true, right?
Okay, say again. Set the BL to
-1 and AL to like 5 or something. It will validate the true, right?
it will continue execution at L1. Correct. Okay. Well, I do want to kind of follow through. Okay. So I know we are running out of time, but because of that question, I do want to kind of follow through with that question because I want to show you what I mean when I said a little bit earlier, set up a 5-line program to test it. So I'm going to use my compare1 program as a basis. I will copy it to compare2. So you might end up with a whole bunch of compare instructions like this. So you mentioned that you were using 5. Okay, let me change the instruction to match exactly what I had in Notepad here. Move the Notepad down so I can see it while I'm typing here. AL percent AL percent BL.
BL is 0? 0?
I can always set it, at runtime.
Oh, okay.
All right. So I put a breakpoint on line 6 right before the compare instruction. The only instruction useful here is the compare instruction. The rest of the program, you can not even have it there. It doesn't really matter. So now that I'm about to execute a compare by instruction, I'm going to use the set command here to set AL to, you mentioned AL to be 5, right? Yeah. AL being 5, and then you want BL to be -1, right? Okay. So we want to see whether the, I forgot to put in the JA instruction, but we can look at the flags and see whether the JA instruction will actually branch or not. Okay, so we'll take a look at that. And then we'll single step, look at the flags. Oh, okay, the A flag is not seen here, so what is going on here? Well, there's no such thing as the actual A flag, okay? The A flag is a combination of the other flags. So if you want to look at the A flag as if it is really a flag, it is the following. Okay, how do you know a number, number X is about unsigned. Okay, first of all, if A is less than Y, then A cannot be above Y. Is that making any sense?
Yeah.
So in order for X to be above Y, X cannot be less than Y. So that means the borrow flag or the carry flag has to be clear. Okay, so we know that the carry flag has to be clear. We're going to use a bar to indicate that the carry flag has to be clear or negated. Okay, but since this is not just saying that X is not less than Y, it is saying explicitly X is greater than Y. What about which other flag is useful? The Z flag. But should the Z flag be a 1 or a 0? Should be a 0. It should be a 0 because we don't want those two numbers to be the same. We want it to be different, and yet X is not less than Y. So we want
It can't be less
this to be
than or equal to Y.
Sorry?
It can't be less than or equal to Y, so the Z flag has to be 0.
Correct. And we have a multiplication in between to mean conjunction. So if you want to kind of imagine that this flag called the A flag, it is the conjunction of not carry and not 0. The L flag, there's no such thing as a real L flag either. The L flag, well, we talked about this already, so this is nothing new. It's really the sign flag, exclusive, or the overflow flag. This is how some people represent exclusive or. What about the G flag? The G flag is related to the L flag. We're using the L flag as if it is the borrow flag, and then we still need to rely on the Z flag. Because the G is for greater than, but it's the signed numbers only. What about the B flag below? This is a trick question.
C has to be 1.
C has to be 1, and it is the same as C. Yep, it is just the same as C. It's just it's the same thing as a C. It's just another name. It's a pseudonym of the carry flag. Right?
So the A flag is set then in just those two conditions?
The A flag is set if and only if the carry is clear and the Z flag is also clear.
So our A flag is set.
So in this case, the A flag is set because both of those other flags are clear. If I had a JA instruction after this, the JA instruction will branch to whatever label you tell me.
And the overflow flag in A case would always be different or always be 0. The overflow flag in A case, if A is set, then I don't think so, right?
It's not a sign interpretation. So when you overflow the law, the problem
I'm kind of some
I just found
dot bash underscore alias and alias is the two commands one for the assembler and one for the I could, there's probably a way to write that we pass the name of the file variable. Yeah, I just use the aliases. Then I only have to type in except.
Okay, well, I'm gonna do the shutdown also. Yeah, go ahead.
I just have to.
Mine's gonna be a little longer.